Today we're going to discuss the relationship between delta G and K. Delta G, remember we calculated last week, was the change in free energy. It helped us figure out if a reaction was thermodynamically favorable when delta G was negative or thermodynamically unfavorable when delta G was positive. K we've talked about before, capital K is the equilibrium constant. We're going to relate them using an equation. The equation that we have is delta G equals negative RT ln of K, so the natural log of K. And this is the relationship. Now, if you notice here, the sign of these, well, we'll check it out. The opposite sign, we have a negative here, so that would be important. Now, if delta G is at equilibrium, then we know that delta G has a value of 0 from what we talked about in the previous video. So that would be in 0 kilojoules per mole reaction. And then we'll put a 0 here. All right, equals negative R is the gas constant, and we're going to use the value that relates to joules. And so we would use 8.3145 joules per moles times Kelvin. Going back over here, delta G, the units for kilojoules here in delta G doesn't match the joules. So we need to make one of them match. It's your choice. In this example, I'll just make the joules match on both sides. So I'm going to multiply this by 1,000. So 0 times 1,000 is still 0. So we still have 0 joules per mole over here for delta G. And so the R is over here. And then the T. So on the other video that we had from the other day, the temperature happened to be for H2O solid ice melting was at 0 degrees Celsius, or at equilibrium. So we have to convert this to make the units match for Kelvin. So the temperature needs to be in Kelvin. So first we have joules per moles times Kelvin here for R. The temperature needs to be in Kelvin, so we can cancel those out. So we add 273 to 0 degrees Celsius, so we have 273 Kelvin. And then if you notice, the joules and the moles, they'll cancel out on the opposite sides, and we'll end up with the natural log of K. Now, if we take a look here, then all we have to do is just solve for K by itself. So what we're going to do is, in this case, we happen to multiply everything over here. So with negative 8.3145 and 273. So we divide both sides by that. So 0 divided by all this is still 0. So 0 equals the natural log of K. And then we raise, to get rid of the natural log, we raise it e to the natural log of K, and the e and the natural log will cancel out. And then e to the 0 is equal to 1. So that means that K is equal to 1 in this case. Now at equilibrium, what we know about K is that reactants and products are both equally favored if K equals 1. And that's what happens. And so when delta G was equal to 0, the K value is equal to 1 because neither reactants nor products are favored, or you could say they're equally favored. Now let's try another example where we're not at equilibrium, where we actually have a value for delta G. Now we have another example where we're given that delta G, we solved for delta G in a different reaction, and the delta G was negative. And from what we learned about previously, then if delta G is negative, the reaction should be thermodynamically favorable at that particular temperature. So let's make the temperature 25 degrees Celsius. This reaction is spontaneous. Spontaneous means that the reaction would occur on its own. Same thing with thermodynamically favorable. It would occur on its own at this particular temperature without outside help or energy. So now let's go ahead and plug and chug then to solve. So delta G is negative 100 kilojoules per mole. That's what we were given. So we're going to do like we did before. For R, 8.3145 joules per moles times Kelvin. So we use this value of the universal gas constant. And then we need to make the units match between joules and kilojoules. So we're going to multiply this times 1,000. And then now we get to joules. So 100 times 1,000 gets us basically 100,000. So I'll put this 100,000. And then we have the temperature. The temperature is 25 degrees Celsius, so we need to convert that to Kelvin. So we have 298 Kelvin. So those units will cancel out, and then these joules will cancel out, and then the moles will cancel out, or the per mole. And then we solve for natural log of K. So now what we need to do is we need to take 100,000 divided by negative 8.3145 divided by 298 and set that equal to the natural log of K. So please try in your calculator while I do this now. So if you notice, the negatives will also cancel out. So I end up with a positive number, 40.3596692. And I want to keep all those digits because once I round somewhere else, it'll actually increase my source of error when I use a natural log and then try to get rid of it. So now what we're going to do is we're going to get rid of the natural log by raising e to the 40.0, and then e and the natural log will cancel out, and we'll solve for k. All right, now we solve for k. I got k equals 3.37 times 10 to the 17th power, which now I can round because this is our final answer here. And I have 3 sig figs because we started off with 100 with the decimal here in our original number. Now, if we take a look at the k value is super huge. It is way bigger than 1. And then remember, k value is greater than 1. That means that products are favored. Products are favored. And this should also make sense because if the reaction is thermodynamically favorable or spontaneous, that means that the reaction will occur on its own. Which way will it go? Well, it'll proceed in the forward direction, and it will make the products. And that's confirmed by our k value here. Now, on the opposite side, what you'll notice is if the delta G is positive, this negative will make the k value, or it'll make this number a negative number. And if I raise e to the negative number, I will get a k value that's less than 1. And then that would tell us that on the flip side, reactants would be favored. So with a negative e value, so if we had a positive sign for delta G, we would actually get a negative number over here for e to the negative power, and then we would have a k that would be less than 1. So if we wanted to recap what we have here, let me go ahead and erase the board. Let's make it simple here. So at equilibrium, we talked about before, k would be equal to 1 at equilibrium, and then the delta G would equal 0. All right, so that's simple. So and then remember, if we plugged and chugged, the natural log of 1 is 0, and then doesn't matter what r and t and the negative are, this part times 0 would get us a delta G of 0, and we would know that the system is at equilibrium. If it's thermodynamically favorable, we know that the sign of delta G is negative, and then the k would be greater than 1 because products would be favored. And if we take a look here, if we take a negative number, the negatives will cancel out. We'll end up with a positive number, and that'll get us a k that's greater than 1. Also, another thing to double check, if we did the reverse, if we natural log a number that's greater than 1, we'll end up with basically a positive number over here on this part, and then delta G would be equal to negative times the positive number. So negative times the positive number is a negative number. That's how delta G would be negative. And then on the flip side then, if delta G is positive, then the k value would be less than 1 because reactants would be favored. And if we took the natural log of a number that's less than 1, we will get a negative number. And so this negative number for ln of k times a negative number for a negative RT with the sign here, negative times a negative will get us a positive for delta G. So from the equation, we can figure out the relationship between free energy and k.